Assalamu alaikum warahmatullahi wabarakatuh. Dear students, this is Dr. Ali El-Moursy and we are in lecture number 27 for microprocessor class. This is actually part 1 of the lecture, and here we want to discuss in some details the hardware of the microprocessor that is in charge of doing the floating point operations. Since the start of the semester till we started the floating point, we was discussing only the x86 machines, the 8086 or 8088, which are actually an integer units, and these are the main processors in the kind of an old PCs. In the last couple of set of slides, we discussed and we explored the floating point as a representation for numbers, and we also discussed how to do mathematics for them. Now it comes to the moment of to see kind of applicability of what we have learned in floating point in the hardware. So this set of slides are actually talking about the x87 floating point unit and its instruction set. Each processor in the 8088 on the 80 in the x86 family, whether it is 8086 or 8088 or whatever, has its corresponding coprocessor. So the main processor is the x86 machine. However, in order to be able to do floating point operations and to deal with floating point numbers, the main processor is not in charge of this. There are other extension processor that is actually in charge of doing those operations. So they call it a coprocessor. In other notions, they call it the math coprocessor, and it takes different names. In some references or in some families, they call it the NPX, stands for numeric processor extension, or NDP, numeric data processor, floating point unit, FUP. So any of those names are actually talking about a coprocessor that is in charge of doing floating point operations. Remember that this cannot be the main processor. So the main processor that is actually going into the cycle of the fetch, decode, execute, as we explained in the early beginning lectures of the microprocessor class, is the 8086 or the x86 processor. But this is kind of a supportive or coprocessor that helps the main processor. So in slide number 3 here, we can actually see kind of mapping between the main processor of the machine and the coprocessor model number. So for 8086 or 8088, we are using what's called the 8087 coprocessor for numerical or for the floating point operations, and with the next generations of the 80 or the x86 machines or processors, each of them has its corresponding processor. Maybe nowadays there is another names that they give to the those coprocessors, the MMX machine or the EES extension. So the later processors use different names for those coprocessors. But since we started all of our class is talking about the 8086 and 8088, so we will go and discuss in more details the 8087 coprocessor. Slide 4 here is actually just show in hardware how the two processors are connected. We have the 8086 processor actually shown here, okay, and it is connected through different wires and buses to the 8087 processor here, okay, and definitely both are connected through some bus, which is actually connect the whole chip to the system bus that connects the chip to the memory. Okay, there are other devices related to the clock generators and the PCI, and this is just give you a general idea about the processor that we have here and how they are connected. Nothing of this you have to memorize, but it's just for your information. So this is actually a picture that's showing the 8087 coprocessor, which is called NPX processor. In this set of slides, we are about to we have the following agenda. We want to talk a little bit about the architecture of the 8087. We want to discuss the data types that it supports, the interface with the end user, and how the end user can control and change the configuration of that processor, and we will discuss a little bit of how to do programming and a few of the set of instructions for those kind of processors. I have to highlight here that we don't have programming problems for the theory for that part of the course. So I will never ask you to write programs for the x87 in the theory. However, we have some labs. In the lab part, we will deal with some programs for the instructions for the 8087 coprocessor. The 8087 processor is kind of an interesting design for a coprocessor, because actually it is dependent or depends on a stack fashion of accessing or generating the different data and instructions. We will discuss this shortly. However, in this slide we are just talking about that this is actually the unit. The x87 is the unit that is responsible for floating point unit and floating point operations, and this is definitely used extensively in all of the scientific and engineering and business applications, which actually needs us to deal with real numbers, not just an integer numbers. It supports different types of floating point. However, this unit is also supporting very lengthy or extended versions of integers and packed BCD integers. However, we will focus only on the floating point representation and the floating point numbers and operations that is performed through this kind of processor. For the floating point, they rely on the IEEE standard 754, which we already covered in our last two sets of slides. Slide number 7 here is actually showing the execution unit and the control unit for the 8087 processors. A lot of details are mentioned here. However, we will not go over all of those details. Again, I don't want you to memorize them, but these pictures are actually showing you some of the internal structures and details of those processors. And as you can see here, you can find here an 8 register stack of 80 bits wide, and this is the most critical information that we wanted to deal with and we learn here, as we will see in shortly in the upcoming slides. There is definitely an internal buses connecting these registers to the functional units that actually perform the operations. The arithmetic modules here is performing the operations. We have some control word and status words that we will discuss them in more details. Mathematics here are too complex because you are doing mathematics for floating point numbers, and you are performing a very sophisticated, complicated operations like calculating the log, calculating the exponential, calculating the powers for floating point, which is extremely difficult in its mathematics, as a matter of fact. That means the status word here is actually important for you to understand how these the type of exceptions or the type of special cases here that you want to deal with are many, and you should have some control over what's going on to know whether the operation is performed successfully or not, as we will see in the coming slides. So the FP execution, or the floating point unit execution, the x87 execute instructions from processor's normal instruction stream, meaning that the major or the main processor, which is the 8086, actually doing the fetch decode steps for the instructions, but at the execution it will when it actually discover that the instruction that it's about to be executed is a floating point instruction, so it will actually send this instruction to the x87 floating point unit coprocessor in order to execute it and return back the results after the execution. We have to note here that since the floating point unit is complex, it takes extensive number of cycles to complete one operation. So if you are assuming that add or subtract for integer taking 1 or 2 cycles, the floating point takes many and many cycles to perform one operation. So the status of the x87 is independent from the status of the basic execution environment. So that's why it should keep some buffers to check its status. It may take a longer time to finish one instruction. So while it is busy doing something, the x87 should indicate to the x86 that he is busy with doing something, and he cannot tolerate or accept more instructions to be sent to the x87 until it finish what's going on or the instructions currently executed. So the x87 is actually representing a separate execution environment from the x86, the main processor. However, here we need actually, so as a matter of fact, we want to discuss two things for the processor as we did for the x86. We need to discuss some of the instructions, okay, in order for us as a programmers to know how to do programming. And more importantly, we have first to understand the registers exist in that processor. Through the registers you can understand what's going on and how to deal with this machine. So actually we can identify a set of very critical registers in the machine here. We have what's called the status register, we have the control register, we have the tag word register, last instruction pointer, last data pointer, and the opcode register. Let us explain each of those registers quickly. The status register is actually indicates whether the mathematical operation is went successful or not. So if you have any error or exception or something abnormal happening, you have to check the status register to see what's going on in the previous mathematical operation, similar to the status register of the x86. Control register, this is actually kind of a new register that is not existing in the what we have learned in the x86 and this actually register allows some configuration for the x87. We will see what kind of configuration that we want to learn or to do for the x87 in the following slides. Tag word register. This is actually some register that actually this we will not deal with that register, so we can just skip it. However, this register is mainly responsible for the accessing the memory if the x86 will access the memory. Last instruction pointer, this is for the code segment in order to allow the x87 to have access to the current instruction that is sent by the x86. The last data operand pointer, this is also a pointer if he wants to access some data in the data segment, he can use this register. The opcode register is actually to hold the opcode for the current instruction. So as you know, like the x86 will not translate or will not decode the instruction for the x87. It will just identify that this is instruction is not an integer, it is a floating point, or it is the responsibility for the x87 to take care of the instruction. So you will send the opcode to put it or store it in the opcode register for the x87 to take care of the translation of the decoding for the instruction and start executing the instruction. Most importantly is in our discussion for the x87 is the data registers. The data registers here have a width of 80 bits. So as we know that the x86 registers are, most of them or all of them are 16 bits, while for the x87 we have here an 80 bits. Okay, so you can perform operations with 80 bits registers in that coprocessor. If you are using the extended version of the register, which is the 80 bits, you can notice here is that the significance or the mantissa is actually 64 bits from bit 0 till bit 63, and the exponent is basically from bit 64 till bit 78, which means 13 different bits, and we have one bit which is the 14th bit for the sign of the mantissa. So it uses an extended version of the IEEE that is not commonly used in by default. We will talk about the different data types of the x87 in the later slides, inshallah. We have the last instruction pointer, the last data pointers. Those pointers can address memory up to 64 bits, okay, and you can actually imagine how much memory area that this could actually access. This is the opcode register, it's 11 bits, and we have 16 bits for the control register, the status register, and the tag register, and those are the registers that we will discuss them extensively. However, we need to indicate that the fashion of accessing those registers, although those registers are named from R0 till R7, this is not the convenient or the default way to access the registers. So it's unlike AX, BX, CX, DX. When you write a program here, you are not just addressing the registers as separated or unique. As you can see here, we have a register which we call usually a register file, which is actually a stack or a bank of registers numbered from 0 till 7, as you can see here. However, in your programming, as we will see here, these registers are accessed in a stack fashion. So the x87 floating point instructions treats the 8 x86 floating point data registers as a register stack. Since we have a stack, we know what's the stack, we know how to access the stack, so the stack is using what we call the push and pop, but this is a stack for registers, so the registers themselves are forming a stack. So that's why the programmer here, when he accesses the registers, he will not use their absolute numbers here. He will use the name st to indicate that this is the stack top. St stands for stack top. So if you are writing the instructions for the x87, you will identify the pointers relative to the top of the stack. st0 is the top of the stack, so we have to have a pointer. So this pointer is pointing to the top of the stack. So in the example shown here, I have R3 on the top of the stack. That's why the top here carries the value 110 to indicate that the top of the stack is register number 3. However, st0, st1, st2 are relative names, so the top of the stack will be always called st0. So whenever you want to access the top of the stack as a programmer, you don't have to worry what is the register number. You just access the top of the stack by indicating st0. If you want to mention the second register of the stack, you will mention st1, then st2, and so on. So the register number for the current top of the stack is stored in what is called the top of the stack, or TOP, which is actually exist in the status register, as we will see shortly. Now, if I wanted to load some data from the memory, into the registers. Remember, here is as we just mentioned, this is actually a stack. So that means this is the top of the stack. Yeah, that means this is the last occupied register. Hold a second. Okay. So actually st0 here is the last occupied register. That means the registers that are occupied with data are those registers. Those registers are full of data. Okay? Agree? So the empty registers, the registers that are not occupied, are the ones after the top of the stack. That's why we are mentioning that the stack here is grow backward, similar to our regular stack. So if I want to push some data from the memory to the stack register here, I am using the load instruction. So the load operation is basically decrement the top of the stack. Okay, so shift the top of the stack one place down in order to point here, and will take the data from the memory, okay, by one, and load a value, okay, okay, into the new top of the stack of register. Okay, and the stored operation will do the opposite, as we will see in the next instructions. Okay, so for the x87 floating point unit, a load operation is equivalent to a push. يبقى load instruction is kind of pushing, and the store يبقى load is push, the store is pop. So that means when I'm loading, I'm effectively ordering the top of the stack to shift one place down and get the data from the memory and put it here in that location. Automatically after I load the data, that TOS or top of the stack will not be at 110. The top of the stack will be at this location of address 2 to R2. R2 means it will have the value 010 in binary. Okay, and this is actually where the new ST0 will be pointing at. يبقى ST0 after loading will not be at register 3 with value 110. It will be at register 2 at 010. This is if I use the load instruction. Okay. Store instruction doing the opposite. It's actually popping. يبقى pushing and popping. Okay. Time. Now, many floating point instructions have several addressing modes. However, the default one is to use the ST0 or the ST notation to access the top of the stack or any previous loaded data. Okay. By the way, you can omit the 0, so ST0 or ST are two equivalent words. So either using ST or ST0. ST means ST0, but if you want to point to ST1 or ST2, you have to explicitly mention that. Okay, so there are other ways to access those registers explicitly by mentioning its name, but this is not the conventional way. So we have here, those are actually called a R0, R1, actually FR0, FR1, FR2 and so on. But this is the convention, this is not the conventional, this is unlikely, unlikely used. The likely used method to access the registers is through their ST names. Okay, so we have ST0 till ST7. However, this is wrapped around, so definitely if I'm here, if I'm at location 3, that means I have basically if I just let me just erase this. So here this example here indicates that ST0, ST1, ST2, ST3, ST4 are meaningful names for the operands of your instructions. It's unlikely to use in this example ST5 because ST5, this is wrapped around, so if ST5 will actually point you to this location, and this location is supposed to be occupied or empty. This is empty because this is actually outside your range. You pushed through the load, you pushed data in those registers only. Okay, so that means those are supposed to be still empty, so it's unlikely in this example that you are accessing ST5. Okay, so you are supposed here to use ST0, ST1, ST2, ST3 and ST4. This is the regular permissible values or logically are likely values to be used. Okay, so now let us take an example for an instruction here to see how things are going. So for example, if the top of the stack contains the value 110 in binary, which means register number 3, the following instruction will do the following. So I have here fadd. As you can see here, I add the letter F because this is a floating point instruction, and this instruction is supposed to add two registers together. Which two registers? ST means ST0, that means the value in register R3 will be added to the value at register R2, and the result of this addition will be placed or stored back. So after this يبقى after this instruction what happens is actually the value of ST0 will be added to the value of ST2 and will be stored at the top of the stack at ST0. Okay, agree? This is just a this will be added to this and will be stored back into number 3. Agree? Makes sense? Okay, now let's move to another register in the x87 processor. The second register that we want to discuss is the status register. Status register is very important. It carries the following bits. Actually, it is the 16-bit, but each group of bits is actually carrying useful information. Okay, so we want to talk about the bits of the status register one by one, and we want to indicate what they are actually doing. Okay, they are numbers from 0 till 15, and they are actually showing some status. The first bit is called the floating point busy flag. Okay, second one is the top of the stack, TOP, that we have just mentioned. So definitely these are how many bits? Those are bits from 11 till 13. 3 bits here are the top of the stacks because we have actually 8 registers. Okay, we have also 4 conditional code bits or flags. These are C0, C1, C2, C3. Okay, these are bits 8, 9, 10 and 14. The error summary status flag. Okay, the stack fault flag and the exception flag. Okay, the exception flags, it's not only one flag, so the last part here is a set of flags. It's not only one, it is a set of flags. Okay, these are actually the bits for starting from 0 till the number 5. Okay, these are 6 different flags or bits. So in the next slides we will actually discuss each of those bits in separate. So let's discuss the first one, the busy flag. The busy flag here is actually indicates that the x87 is busy doing some calculations and he is not ready to communicate with the x86. So x86 should check this flag before sending or receiving data from the x87 processor. The second set of bits here are the top of the stack, as we indicated. We discussed them in the explanation of the registers. The next 4 flags are 4 conditional flags. These are actually C0, C1, C2, C3, and those are basically conditional code flags that are responsible to control the conditional jump instructions, similar to the bits that we have discussed for the conditional jumps for the x86. We have the 0 flag, the sign flag, the overflow flag, the carry flag. Okay, so it is actually to control the conditional jump instructions for the floating point instructions. The ES, which is actually the error summary flag. Okay, so that means if the last operation have ended up of any error, okay, this flag will be raised to 1. Stack fault flag, this actually indicates that you start overflowing the flag. So if you keeps pushing of the register values, loading from the memory, that means you will get your register full, and this actually will makes this flag pops out to you, indicating that you have stack overflow for the registers. The exception flags are actually indicating, as you can see here, those flags are more than what we have, or those are actually a new set of flags that actually to indicate that whether you have one of those errors happening or not, in order to allow you to take care of one of those different sets of 6 different errors while you're doing floating point calculations. We will discuss each of those in separate in the following set of slides. So top of the stack, a pointer to the x86 floating point data registers, as we explained, that is currently at the top of the x87 execution stack. It contains the bits 11 through a 13 in the status register. This pointer, which is commonly referred to the top of the stack, and has the binary values from 0 till 7, as we explained. The 4 conditional code flags from 0 through C, C0 through C3, indicates the results of the floating point comparison and the arithmetic operations to actually allow the conditional jump instructions to work. These conditions bits are used principally for the conditional branches, as we just explained. Okay. Type. Next is the exception summary. So if there is any exception means error happening in the calculations, this flag will give you the summary that I have one of the errors is happening. So the summary bit is actually will be set when any of the unmasked exceptions flags are set. So when the ES flag is set, the exception handling is invoked. So this allows the exception flag to be invoked. We will talk about the exceptions or the interrupts, the mathematical interrupts, inshallah, in the interrupt chapter, when we go to the interrupt chapter. So right now we will just mentioning what this flag is doing, and we will elaborate more in that in the interrupt chapter. So the 686 floating point exception flags are bits from 0 till 5, and they are actually indicates one of the individual exceptions that can happen here. Okay, they are 6. They are called the I, E, D, E, Z, E, O, E, U, E, and P, E. They are the actually for the exceptions for the precision, underflow, overflow, zero divide, denormalized operands, invalid operations. Type. To go into more details discussing those flags, so let's go and discuss each of those exceptions in separate. The first exception that we want to discuss is what's called the precision error. The precision error, we indicate or we mention that the registers of the x87 are 80 bits. However, there are different modes that you can run this processor through. So this processor can work either for single precision, for double precision, or for extended precision. If you have exception in the precision, that means you are dealing with 2 registers with different precisions, or for the memory and the register with different precisions, the precision error will be indicated. Okay, so that means this also may indicate that if you change the precision, you may get a correct answer. Okay, so the second flag is what's called the underflow error. As we indicated that for floating point, the smallest number ever that we can represent, if I am using a single precision, we already indicated, we actually discussed that in our last set of, so for single precision, for single precision we have actually, okay, the minimum number to be represented, if you still remember, is 2 to the power minus 144. 49. Okay, so if the number that is generated even smaller than that, that means you have an underflow exception. That means the number is smaller than the number that you can represent by the single precision. So that means you may go to a higher precision to execute your instructions. The next one is the overflow. We know all what's overflow. If the number is bigger than what you can represent, again for the single precision definitely it is a, we mentioned it's using 32 bits for the registers or for the values. Okay, single precision is 32 bits. So for 32 bits the overflow happens if the number exceeds the if I recall, it was 2 to the power 128. So the largest number ever that you can represent is 2 to the power 128, almost 128, almost. Okay, this is the largest ever number. So if your number is higher than this, that means you will have an overflow happening here. You have an overflow case, and you have to go into maybe a higher precision. So we as we will see shortly, we have what's called the single precision of 32 bits. We have the double precision for the 64 bits, and we have the extended precision for the 80 bits. Okay, we will see this shortly in a minute when we go to the control register. Okay, then we have the zero error. If you are dividing by 0, this is actually will pops up to give you an error. Denormalized error means that at least one of the operands that you are dealing with is denormalized. So that means you have to make sure that you are dealing with denormalized numbers. Invalid error, this can happen with different so if you are doing calculations with not a number, we mentioned that we have the range of values for not a number, and if you still recall, the not a numbers have the e should be all ones. Okay, for the e, however the fractional mantissa will have any value. Okay, so this actually any combination of this means that the number that I have here is not a number. If you are performing any mathematical operation with not a number, so the invalid error will occur to you. However, this also this flag will be raised if you are dealing with an invalid opcodes for the floating point. So this flag indicates such that the produce taking a square root for a negative number. So it's another example here for an invalid operation. You cannot get you can get the square root for a negative number. So this exception will also be raised. Okay, so we will stop here for the part number 1 of 27, lecture 27, and we will continue in explaining the rest of the control register and giving some example of instructions how to deal with the stack of registers for the x87 in the lecture 27 part 2, inshallah. So we will stop here and we'll take a little bit of break, and we will continue inshallah with the second part of this lecture. Thank you.